Compound interest. Our objective, we want to find the future value and the present value of investments that involve compound interest. Well, let's remind ourselves that we know what an exponential function is because these formulas are exponential functions. Any function of the form f of x equals b to the x, where the base is a positive number but not equal to 1, and the exponent, which is our variable, is any real number. Okay, as I just stated, compound interest formulas are examples of exponential functions. The exponents are variables, and you can see with these three formulas here, time is the independent variable, and time is the exponent here, here, and here. This is why these are exponential functions. Okay, so the future value, how much will I have in the future? If I deal with compound interest, well, there are three possible formulas for the future value. We'll do an example that talks about two of them. The first formula deals with annual compounding that is once a year. The second formula deals with a defined number of compounding periods per year. For example, monthly or daily compounding. And the third formula deals with continuous compounding, compounding without bounds. All right, in all these formulas, the S is the future value, the ending amount. The P is the principal, the amount you're investing, or the beginning amount. The R is the annual interest rate in decimal form. The T is the length of time in years, and the K, which appears in this formula, is the number of times we're compounding per year. Okay, so for annual compounding, the amount in the future equals the amount that you invest times 1 plus the rate as a decimal raised to the number of years. For K compounding periods per year, the future value is equal to the present value, the principal, the amount you invest, times 1 plus the rate as a decimal divided by the number of times you're compounding per year. All of that raised to the product of the number of times compounded per year times the number of years. And for continuous compounding, whenever you see the word continuous, you need to automatically say to yourself, this is going to involve Euler's number E. Every time continuous is invoked in mathematics, it will involve Euler's number E every single time. So just get that into your head. That's a connection. Continuous means E. If I see an E, I'm doing something on a continuous basis. And the formula for continuous compounding is the future value equals the amount you invest, or the present value, times Euler's number E, raised to the rate times the number of years times the time. Okay, let's do an example of this one. I'll leave those formulas right up there for us, I hope. And we're gonna focus on the bottom two formulas for this one, for this example. You decide to invest $8,000 for 6 years, and you have a choice between two accounts. The first account pays 1.2% per year, so I'll make a note of that. And we're going to compound monthly. 1.2%, and we're going to compound monthly. The second account pays 1.19%, so a little bit less it's paying, so 1.19%. However, it is compounding continuously. It's compounding more often than 12 times per year. It's compounding all the time. So this account is compounding continuously. Okay, which one's better? So the first account has a slightly higher interest rate, but the second account is compounding more often than this one is. So which one turns out to be the better choice? Well, let's first start with this one. We're compounding 12 times per year. So for K compounding periods per year, we use this formula, and in our case, K is 12. So our ending amount, our future value, equals our beginning amount, which is $8,000, times 1 plus the rate as a decimal. Let's remind ourselves that 1.2% is 0.012. Percent means out of 100 or divided by 100. And when you divide by 100, the decimal moves 2 places to the left. So we're going to put 0.012 in the numerator. K is the number of times we're compounding per year. Compounding monthly means we're compounding 12 times per year. Raised to the K, which is 12, times T, the number of years, well, we're doing 6 years. There we go. There's our formula with the variables filled in. This is just simply a calculation. So let's pull out a calculator, and out comes $8,000, $8,596.93. We'll round to the nearest penny. As a reminder, that's the penny place right there. So round to that, the 100th place here. So we just figured out that in choice account number 1 here that pays 1.2% and compounds monthly, our $8,000 will grow after 6 years to $8,596.93. How about if we compound continuously at a slightly smaller interest rate? Well, continuous, again, connect with your brain. Continuous means there's an E involved. So here's our formula. Okay, so S is equal to the principal, the amount we're going to deposit, which is still $8,000, times the letter E, raised to the rate. Well, the rate here is 1.19%, and that is 0.0119 as a decimal. If we're going to do math with it, it needs to be in decimal form. Again, percent is out of 100, or mathematically divided by 100. Dividing by 100 moves the decimal 2 places to the left. So up here is 0.0119 times the time in years, and the time in years is 6. I have a calculation. I'll just pop it into a calculator, and out comes the final amount, the future value, $8,592.09. So we deposit $8,000 into this second account, pays a little bit less interest rate, but is compounding more often. We come out with $8,592.09 6 years later. Which is the better investment? Well, this one is by just about $5. Okay, we'll make a note of that. The 1.2% compounded monthly is the better investment. So there you have it. Working with the compound interest future value formulas. Now let's look at present value. How much money do I need to deposit today to have an amount of money in the future? That's what present value is. Okay, get myself straightened out here, get my notes together. Okay, what is the lump sum that will give me a future value given n compounding periods at a rate I per period? Okay, that's the present value. How much do I need to put away today, okay, to have a known amount in the future? All right. Now here's a good example of that, to give you kind of a sense of how this works. Grandparents are deciding to put a lump sum of money into a trust fund on their granddaughter's 10th birthday, so that when she turns 60, she has $1 million. Nice grandparents. Okay. And the fund will pay 11%. It compounds monthly. And their question is, we want to do this for our granddaughter. How much money do I need to put into the account today in the present in order to come up with $1 million in the future. And we're going to round up the answer to the nearest dollar. We're going to round it up to the nearest dollar. Okay, round up to the nearest dollar. All right, so again, nice grandparents. Their granddaughter is going to turn 10. They have found this fund that pays 11%, that compounds monthly. And their question is, we want her to have $1 million when she turns 60. That's 50 years from now. How much do we need to put in today, in the present, so that she will have $1 million in 50 years in the future? Okay, so notice N is the number of compounding periods and I is the rate per period. So we have to do just a touch of math before we can use this formula. I'll write the formula down. Okay, so let's see here. So I, the rate per period, that's key here. Okay, so I, it's 11% per year, but there are 12 periods. So the rate per period is the annual rate divided by the number of periods per year. And I'm going to write this as a decimal form, 0.11 divided by 12. And I'm going to leave that. I'm going to leave that number just like this. I'm going to put this into my formula for I because this is the exact value. Now let's make a note. If we put that into a calculator, and I need to do that, so give me a moment here. We come up with 0.00916 repeating. So it's a repeating decimal that goes forever. You could go out 5 or 6 places and use that number as an approximation. I would rather use the exact number in my calculation. So I'm going to use I as 0.11 over 12, but you could go 0.009166667 or something and put in like 8 or 9 decimal places, and you'll get really close. Just don't cut it too soon, because the more you truncate, the more you round, the further off your answer is going to be. So that's I. N is the number of compounding periods. Well, we're compounding 12 times per year, and we're doing that for 50 years. Remember, 50 is her 60 minus 10. They want her 60th birthday. They're starting at her 10th birthday. There's your 50 years. So we're going to multiply 12 times 50, and we have 600 compounding periods. Okay, we had to come up with that number as well. So, and we know how much we want. That's $1 million. So that one's done. But we had to do some math to get our interest rate per period per month. And we had to do a little bit of math to get the number of compounding periods we're talking about. And so now we have those. So P is equal to, we want $1 million. So we'll put $1 million at the top line here in the numerator. And then it's 1 plus I, and I've chosen to leave I in its exact form, 0.11 divided by 12, raised to the N, number of compounding periods, which is 600, into a calculator, and then round it up to the nearest dollar. Well, that goes into a calculator, and I round it up to the nearest dollar, and the answer is $4,191. How nice is that? These grandparents have just discovered that in this situation, 11% compounded monthly, if they put $4,191 into this account today, and they let that money sit for 50 years, their granddaughter is going to have $1 million when she turns 60. Pretty impressive, the power of compounding.